While this is a simplistic view of how electricity gets to you after it leaves the plant, the voltage is basically stepped up by a substation transformer. It then goes into transmission lines. These are basically the superhighways that transport electricity over long distances. Structures are picked based on the amount of voltage that's being transported and the terrain that's being served. As you can imagine, that can vary widely, and transmission is built and maintained in some pretty tough spots. Significant stakeholder buy-in goes into transmission route planning and ongoing maintenance. According to the Edison Electric Institute, the U.S. electric transmission grid consists of approximately 200,000 miles of high voltage lines. Those are 144 kilovolts or more. Redundancy or backups are built into the transmission system so that there are other power plant paths available in emergencies and to efficiently access electricity generation. This is even done across different power providers. The U.S. power grid is actually made up of 3 large interconnected systems. These are the Eastern, Western, and Texas interconnections. This is so the electricity can be moved around the country. In other words, electric transmission and distribution lines owned by an individual utility are no longer used by just that utility. Without a reliable transmission system, we would not have reliable power distributed to our homes. Standards are in place that have been approved by the Federal Energy Regulatory Commission. They regulate the transmission system in the U.S. They're an independent agency that regulates interstate transmission of natural gas, oil, and electricity. Despite the backup paths, there are some pretty big challenges to managing a transmission grid of this size. These include getting approval from multiple stakeholders to access the land, including tribal land. Also, calculating a fair way to recover construction costs when transmission lines are built in one state but benefit customers in a totally different state. Making sure transmission lines are constructed to reach renewable energy is another issue. A big challenge is that often wind and utility-scale solar are not built in population-dense areas where the electricity is actually used. That means it needs to be transported, and in many cases the transmission lines don't yet exist. And last but not least, protecting the grid from natural disasters, both physical or cybersecurity, is also something stakeholders worry about, including who has ultimate authority from a governance standpoint.
Until about 2005, we witnessed a decline in investment, a deterioration of the high voltage grid at a time when the electric system and the economy were just beginning to become transformed into something we have today. We have, of course, more renewable energy, and as capital costs come down and the costs of producing wind power and solar biomass power, there's more of it, and it completely transforms the nature of the whole electric system and how it operates.
Right now, transmission congestion is held up as one of the biggest issues or concerns in the U.S. industry. Even if we built a lot of renewable energy, we need to figure out a way to move it across long distances and even across state lines. After the transmission lines carry the electricity long distances, as you heard, the power is stepped down again through a neighborhood substation transformer. It's then carried across distribution lines that carry the electricity to our homes and businesses. Transformers on the poles actually step down electricity once again, and that's to ensure it's at a safe and usable level in our homes and businesses. While beauty is in the eye of the beholder, many people don't like the appearance of distribution lines or transmission lines. They also feel that burying distribution lines not only solves this issue, but also helps avoid outages. So why aren't they all just buried? That's a question I get a lot. The simple explanation is that it's a matter of cost. In many cases, it's cost prohibitive to bury power lines. According to the U.S. Energy Information Administration, the cost of underground power lines can be 5 to 10 times that of overhead. The amount varies considerably by geography, though. So Florida has a high water table, and the Rocky Mountain region has a lot of granite bedrock. This makes burying those lines not just expensive, but sometimes not even possible. Here are some real-world examples of the impact that this could have on customers' bills. The effect of undergrounding on a customer's utility bill depends on the characteristics of each unique project. Let me show you a range of some effects. There was a 2010 study that assessed undergrounding options requested by the District of Columbia's Public Utility Commission, and they found that burying all overhead equipment would cost $5.8 billion. A local utility official later stated that this would add $226 to the average monthly bill over 10 years, or $107 a month for 30 years. Let me give you another example. After a series of storms, North Carolina looked at the costs of undergrounding the state's distribution infrastructure, and they found it would raise electricity rates by over 125%. Anaheim, California decided to completely convert its system for aesthetic reasons. To minimize the impact on customer bills, undergrounding is taking place slowly over a period of 50 years, and it's funded by a 4% surcharge on electric bills. Another thing to consider is that underground lines are more difficult to locate and repair in the event of an issue. So as we've seen, there's more than meets the eye, even when it comes to the infrastructure of this industry. And it pays to look at the impact of decisions on costs and reliability.